In my opinion, Schaublin make the best small lathes in the world, but unless you have roughly 50 grand or so to put towards one of these machines, buying new isn't viable. I bought this machine second hand for a small fraction of this, and that's because it was in an unusable condition. In this video, we revived this lovely but knackered watchmaker's lathe, and in a way that doesn't just make it look pretty, but with a goal to restore the machine to its original level of precision. The slideways and headstock bearings were badly worn, the ball handles were bent, and the feed screws had about half a turn of backlash. Although functionally irrelevant, the paintwork left something to be desired, so we will have to do something about that too. This is the compound slide, which is used to traverse the tooltip. Unlike the majority of larger lathes, the compound slide assembly can be easily removed from the machine, which is very useful for fitting other attachments, cleaning or setting up. Let's begin our restoration journey here. The first job is to dismantle the top slide assembly so we can access the critical surfaces. This brings me to one of my favourite techniques, metal scraping. In the modern day, this technique is somewhat forgotten because in industry we can now rely on the accuracy of expensive machines to achieve very high tolerances. Scraping, however, allows me to carefully remove tiny amounts of metal in targeted areas so I can achieve extremely accurate tolerances. I've been scraping for as long as I can remember because it's such an affordable way to make machines accurate and therefore produce good work. The idea here is we take a reference surface that we know is flat and cover it in a thin layer of blue paste called engineer's blue, not to be confused with layout blue. There is a little bit more to it, but in essence the blue is transferred to the spots of the workpiece that are high, which we can then remove with a scraper. The process is repeated until a flat surface is achieved. Here you can see the top slide needs a lot of scraping. These dovetails are an unusual angle and not the traditional 60 degrees, so I made this straight edge from cast iron. The slideway dovetails were absolutely knackered, and access to these surfaces was a challenge with the scraper. So I set up the top slide on the milling machine to grind the dovetails close, where I could then finish them up with the scraper. This is Alistair's milling machine, and he has also spent many hours scraping the slideways, so we can be confident they make a good reference. As I traverse the top slide, watch the indicator needle. You can see the slideway has worn with an S shape. As I mentioned at the start of the video, the feed screws and feed nuts were very worn. When new, these were beautifully made things. The feed screws were hardened and ground, so I attempted to revive them by lapping the thread and then making a tap to fit the thread. In the end, I gave up on this because the feed screws were just too far gone. So instead, Alistair and I teamed up to tackle this by remaking the worn parts from scratch. We machined replacement feed nuts from phosphor bronze and then carefully screw cut the feed screws from EN8M steel. Here's the problem. To do this properly, they should really be heat treated, but the heat treatment causes the metal to distort. In industry, this is overcome by heat treating first and then grinding the thread form into the already hard blank. We aren't really set up for this process, but Alistair devised a workaround and it works surprisingly well. Firstly, the feed screw is machined in the soft steel and then mounted in the milling machine spindle. The heat treatment is done with the spindle slowly rotating to even out the heat application and quench. As you can see, with this method the screw stays dead straight. There were a few other jobs to do, such as straightening the handle and remaking the guide bushing, which I did off camera. Once assembled, the top slide works gorgeously. The slideway is now accurate, free moving with no tight spots or slop, and the backlash is around 10 microns. I repeated the process with the cross slide. As I proceed with the scraping, the blue spots get smaller, so it slows down. It's tiring work, but with this simple technique I can achieve a precision that can otherwise only be matched with the best precision grinding machines in the world, albeit it takes me a few hundred times longer. Here I'm using a comparator to check parallelism as I scrape. It's easy to get lost in scraping off all the little blue spots and then forget about the other variables we need to control. A holistic approach is essential to achieve an accurate result. For example, we could carefully scrape the slideway dovetails flat, but if they aren't parallel, the slideway will be sloppy at one end and then tight at the other. Here you can see the slideway now moves freely and smoothly with minimal sideways play. I'm going to stop here for now. You can just about see there is a small patch that I haven't yet completely removed all the scoring from. As I use the machine, it will get worn again, so I will keep the slideways in good condition by rescraping every couple of years or so. These remaining wear marks will be removed on my next scraping session, but we still have a lot of work to do on the rest of the machine, so I better get a move on. The bed needed a lot of scraping, and there are some marks, such as hacksaw slips, that will unfortunately remain in this bed forever, because they're just too deep to remove. Weirdly, although they should not have been subject to significant wear, the feet on the underneath of the bed were not at all flat, so we mounted the bed upside down on the milling machine and addressed this issue. I changed the original countershaft unit for a later one, designed for a slightly larger Schaublin 70. This larger lathe used a flat belt pulley, so I turned a new pulley to pair with the lathe spindle pulley. I wired up the motor and turned it on. After about 3 glorious seconds of the motor running, it abruptly stopped and began spewing smoke. It turns out the insulation on the wiring was unfortunately damaged, causing an internal short. I sorted this out with some heat shrink, and then we were up and running again. I reassembled the lathe and used it in this condition for a while. You can see it in operation in our previous 2 videos, so please do check those out. At this point, I was actually pretty happy with the functionality. The scraping on the tool post mounting surface wasn't quite right though, because of a repair made by a previous owner. The central part had been replaced with mild steel, presumably due to a cracked casting, and unfortunately mild steel doesn't scrape very well, so I face milled and lapped this surface flat instead. The shielding on the spindle had seen some abuse, so this was skimmed up in the larger lathe. I cleaned up some various other components too, such as the pulley wheel and the ball handles. I actually addressed every single component, right down to the smallest bolt, but I was also careful to avoid touching critical surfaces, such as the tailstock barrel, which needs to be a precise fit in the tailstock casting. Now it's time to move on to painting. Here I plugged up critical holes before stripping off the old paint to keep them free from grit and paint flecks. I use a variety of techniques to remove the old paint. Here I'm using a scraper on the tailstock casting. In some cases a wire brush on the drill worked better, and for bits I couldn't easily access with these 2 options, I used a sandblaster. I don't have a closed cabinet type sandblaster, so to minimise mess I only use the sandblaster when necessary. Before I start priming, I like to fill in the castings with filler, so I apply this liberally and then sand down. Now I begin to build up layers of anti-corrosive zinc phosphate primer. Sometimes I switch primer colours to make it easier to see where I've sanded between layers and how subsequent layers then go on. I use enamel paint for the top coats, and I keep applying layers until I'm happy with the finish. To complete the paintwork, I hand paint the lettering on the front. So there's just one more thing to sort before we move on to final assembly. During the past few decades of use, the spindle bearings have become quite worn, and it's vital that the spindle bearings are accurate to produce good work. So I carefully lapped the spindle and then used it as a reference to scrape the bearings. This is the same principle as I demonstrated at the start of the video, but in this case it's for curved surfaces as opposed to flat ones. Modern lathes, including the new Schaublin machines, tend to use ball bearings, but it's not clear if these are actually advantageous over a precision hydrodynamic bearing, such as the ones you see on this machine. For example, take this precision dicing machine owned by the University of Southampton. A dicing machine is a type of precision CNC grinding machine, typically used for cutting silicon wafers. In fact, I've used this very machine to grind microscopic features into fibre optics, so the spindle bearings need to be accurate for this sort of work. This spindle is supported by air bearings and not ball bearings. Air bearings work in a similar way to the hydrodynamic bearings on the Watchmaker's lathe, but rather than supporting the spindle with a film of oil, a thin layer of air is used instead. Ball bearings are a great invention, and because there are no sliding surfaces, friction is reduced. But this comes at the cost of rigidity, because the balls within the bearing race contact over a very small area in the raceway. So to achieve similar levels of rigidity, much larger diameter bearings need to be used. Additionally, the bearing circularity is restricted to the accuracy of the grinding. The good news though is that modern grinding techniques are very good, so it's not usually an issue unless you are chasing extremely high tolerances. Okay, so now the bearings are all scraped, I check the clearances using an indicator. It's important to leave a few microns of play in the spindle so that there's room for an oil film. Too little clearance will result in a high shear rate in the oil film and the bearing could overheat. Too much clearance and then we lose rigidity and therefore precision, so I measured these clearances carefully. I couldn't be happier with how it turned out. Having carefully checked for accuracy, I'm really impressed with just how good it is despite its age. I fitted a stereo microscope to help with machining those fiddly little components, and I made a dividing attachment for the headstock and an overhead pulley system to drive a milling spindle. With this setup, I can make a lot of parts. Before we finish this video, I wanted to announce that we are starting a Patreon channel. This will include extra video content on machining, engineering, science and electronics. We are also writing supplementary articles about our projects and the behind-the-scenes work that goes on in the Cronova workshops. If you fancy trying to replicate some of our projects, drawings and instructions will be available for download. If you are interested, we would be hugely grateful for your support, so please check out the link in the description or the comments section. Thanks for watching, and we'll see you in the next video.